We're constantly surrounded by movement, aren't we?
Yeah.
From just a casual walk to a car speeding past, we sort of intuitively get that things are moving.
Hmm.
But there's quite a bit more science under the surface. So today, we're doing a deep dive into something really fundamental: motion in just one dimension.
Just along a straight line, basically.
Exactly. Movement along a straight line.
Yeah, and we've pulled together some really good educational materials here. The idea is to really nail down the core physics concept.
Right.
Our mission for this deep dive, if you like, is to give you a really clear, hopefully engaging understanding of these basics. It's about building that solid foundation.
Whether you're just curious or maybe need it for, more advanced stuff later.
Exactly. Solid footing.
Okay, so let's kick things off. A really basic but super important distinction our sources make right away: scalar versus vector quantities. What's the core difference there?
Well, think of it like this. Some things in physics, they just need a number and a unit. That's it. That's their magnitude.
Yep.
Mass is a great example. If I say 10 kilograms, you know exactly what that means. Our sources also mention things like, length, time, the total distance you walk.
It's just how much.
Just how much. They're complete with just that value and the unit.
Got it. Then we have these vector quantities. Sounds like there's an extra piece of information involved.
There is. With vectors, you need that magnitude and unit, sure, but you also need a direction.
Ah.
If I just say something moved, say 5 meters, you'd immediately ask.
Which way?
Right. Which way? So displacement, which is related to distance, we'll get there, velocity, acceleration, these are all vectors. Force, too.
Right.
Push or pull. The direction is absolutely critical.
Yeah, I can see how direction changes everything. Now, the materials mention that the magnitude of a vector, the number part with its unit, is always positive.
Mm-hmm.
But we often talk about things like negative velocity or negative acceleration. How does that work?
Yeah, that's a really good point. The negative sign, when you see it with a vector, it's simply telling you the direction. It means it's acting in the opposite direction to whatever direction we've decided is positive.
Okay, so it's a convention.
Exactly. A
Yeah.
convention. If we say moving right is positive, then a negative velocity just means the object is moving left. The how fast part, the magnitude, is still positive. It's just a way to keep track along that single line.
That makes sense, like coordinates on a line. Okay, let's shift gears slightly. Rest and motion seems simple, right? But the sources suggest it's irrelative.
It absolutely is. It all depends on your point of view,
Yeah.
your frame of reference. An object is at rest if its position isn't changing compared to its immediate surroundings.
Like this microphone relative to the desk.
Perfect example.
Yeah.
It's at rest relative to the desk, relative to this room. But if someone's on a moving train looking in the window,
Then the mic is moving relative to them.
precisely, because the train, their frame of reference, is moving. So rest and motion aren't absolute. They depend on who's observing and how they're moving.
Okay, it's all about the comparison point. The materials also bring up this idea of a point particle. That sounds like a major simplification. Why do we do that? Is it useful?
Oh, it's incredibly useful. It's a simplification, yes, but a powerful one, especially when the distances involved are just huge compared to the size of the object itself.
Like a car driving across the country.
Exactly. Or think about a plane flying from London to New York. For tracking that overall journey, treating that big airplane as just a single point makes the maths much, much simpler.
Right.
We can focus on the important bits, where it started, where it finished, how fast it went, without getting bogged down in the details of the wingspan or the tail fin for that specific calculation.
It cuts through the noise, basically.
It's us see the core motion, yeah.
Okay, so then we get to one-dimensional motion itself. The name kind of gives it away, doesn't it?
It really does. One-dimensional motion, or you might hear it called rectilinear motion. It's just movement along a single straight line. That's it.
So a train on a dead straight track, or dropping a ball straight down.
Perfect examples. No sideways curves, no up and down that isn't along that initial line. It's different from, say, a car turning a corner that's 2 dimensions, flat plane.
Or a fly buzzing around the room.
That'd be 3 dimensions.
Yeah.
Yeah. So for this deep dive, we're sticking strictly to that one straight path. Keep it clear.
Straight lines only for today.
Nah.
All right, next up. Distance versus displacement. Now, these are words I know I use interchangeably in everyday life, but physics draws a line between them.
A very important line, yes. Distance is, it's the total length of the path you actually travel.
Okay.
If you take a winding scenic route, the distance is the entire length of that wiggly road you followed.
Got it. The whole journey.
The whole journey. Displacement, on the other hand, is the shortest straight line distance between where you started and where you ended up. And crucially, it includes the direction of that straight line.
Ah, so it's like an arrow pointing from start to finish.
Exactly like an arrow.
Yeah.
It has magnitude, how long the arrow is, and direction, which way it points.
The sources mention a figure, like someone walking a curved path from A to B.
Right, figure 2.2. You can picture it, the distance is the length of that curve they walk.
But the displacement is just the straight shot from A to B.
Precisely. And this really flags the key difference. Distance is scalar, just a magnitude, always positive because you're always covering some ground.
Can't have negative distance.
All right. But displacement is a vector. It has magnitude and direction. So it can be positive, negative, or even zero.
Zero. How can displacement be zero if you moved?
Think about walking around the block and ending up right back at your front door. You definitely walked a certain distance, right?
Sure, maybe half a mile or something.
Exactly. But because your start point and end point are the same place, your displacement, that straight line from start to finish, is zero.
Okay, that makes sense. Distance cares about the whole path. Displacement only cares about the net change from start to end.
You've got it. The sources give other examples too, like someone walking east, then north. The distance adds up, but the displacement is that diagonal line northeast.
And the classic one, throwing a ball straight up in the air.
Perfect. Goes up, say, 3 meters and comes back down 3 meters. The distance traveled is 6 meters.
But it lands back in your hand.
So the displacement is zero. Start and end points are identical. Our sources summarize this nicely in a table, actually. Distance. Scalar, path-dependent, always positive. Displacement, vector, path-independent, only start head matter, can be plus blank or zero.
Tables are good. Visual comparison helps. Okay, let's move on to speed and velocity. Another pair often used interchangeably. Same kind of scalar vector distinction.
Exactly the same kind of distinction. Speed is how fast you're covering distance. Velocity is how fast you're changing your displacement.
So speed is the rate of change of distance.
For unit time, yeah. Meters per second, miles per hour.
And velocity is the rate of change of displacement.
Per unit time, and crucially, in a specific direction. So speed is scalar, velocity is vector.
Okay, that direction thing again. So if I drive around a circular track at a perfectly constant 50 miles per hour...
Your speed is constant 50 miles per hour.
But my velocity...
is constantly changing. Because your direction is constantly changing as you go around the circle.
Ah, right. That's a really clear way to put it. Now, what about when things aren't constant? Uniform and non-uniform speed and velocity.
Right. Uniform speed means you cover the same distance in every equal time chunk. Think cruise control on a perfectly straight highway.
Steady speed.
Steady speed. Non-uniform or variable speed is when that changes. Unequal distances in equal time intervals, like city driving, speeding up, slowing down.
Makes sense.
And for variable speed, we often talk about two things. Instantaneous speed, your speed at one specific moment, like glancing at the speedometer.
Right now.
Exactly. And average speed, which is the total distance you traveled divided by the total time it took.
Got it. And if the speed is uniform, those two are the same.
If the speed is perfectly uniform, yep, instantaneous speed and average speed are identical.
Okay. And does velocity have a similar breakdown? Uniform, non-uniform, instantaneous, average.
Absolutely. Uniform velocity means constant speed and constant direction. So moving in a straight line at a steady pace.
Okay. Stricter condition than uniform speed.
Much stricter. An example might be a raindrop falling at terminal velocity, constant speed downwards once air resistance balances gravity.
Ah, interesting. And non-uniform velocity.
That happens if either the speed changes or the direction changes, or both.
Like our car on the circular track again. Constant speed, but changing direction.
Exactly. That's non-uniform velocity. Or a car speeding up in a straight line, change in speed, same direction.
Oh.
Also non-uniform velocity.
And instantaneous and average velocity.
Same idea. Instantaneous velocity is the velocity, speed, and direction at a particular moment. Average velocity is the total displacement divided by the total time taken.
Total displacement, not distance.
Crucially, yes. Total displacement divided by time.
So, back to the person running a lap on a track. They have an average speed because they covered distance.
Definitely. Let's say they run a 400-meter lap in 60 seconds. Their average speed is 400 divided by 60 meters per second.
But their average velocity for that lap?
Zero. Because their displacement for the full lap is zero. They end where they started. Total displacement is zero, so average velocity is zero.
Even though they were clearly moving.
Exactly. It highlights that difference. Average speed tells you about the overall effort or ground covered over time. Average velocity tells you about the net change in position over time. Again, the sources often use a table to compare speed and velocity point by point. Super useful.
Definitely helps keep it straight. Okay, we're building this up nicely. We know about position, how it changes displacement and velocity.
Yeah.
What about how the change itself changes? Acceleration.
Right. Acceleration. This is the rate at which an object's velocity changes over time.
Rate of change of velocity.
Precisely. How quickly is it speeding up, slowing down, or, importantly, changing direction?
Ah, direction change counts too.
Absolutely, because velocity includes direction. If velocity changes, you have acceleration. Numerically, it's the change in velocity, final velocity minus initial velocity, divided by the time it took for that change.
The formula A.
That's the one. V for final velocity, U for initial velocity, T for time, and the standard unit is meters per second squared, MSS.
Meters per second squared. What does that mean intuitively?
It means the change in velocity in meters per second every second. So if acceleration is, say, 2 meters a square, it means that for every second that passes, the object's velocity increases by 2 meters per second.
Okay, that clarifies the unit. Now, what about retardation or deceleration? Sounds like slowing down.
It is. Retardation or deceleration is simply acceleration that acts in the opposite direction to the object's current velocity.
So it opposes the motion?
Effectively, yes. It causes the speed to decrease.
Yeah.
If an object is moving in the positive direction, a negative acceleration means it's slowing down. We call that retardation.
The sources give some examples, right? Like a car speeding up and then braking.
Yeah, good clear ones. A car starting from rest, initial velocity u equals 0, and reaching 20 meters, final velocity v20, in 10 seconds. The acceleration A would be 10, 10 equals 2 meters 0, positive acceleration speeding up. Then maybe later, the car is moving at 25 meters, u25, and brakes to a stop, v0 in 5 seconds. Now acceleration is 0, 20, 4 meter, 25 meter stall.
Negative acceleration. Slowing down.
Exactly. That's retardation or deceleration in action. Magnitude is 5 meters sojo. But the negative sign tells us it's opposing the initial velocity.
And acceleration is also a vector?
Yes. Very important. Acceleration is a vector quantity. Its direction is the direction of the change in velocity.
The change in velocity.
Okay.
Now, this is a subtle point, but really crucial. Acceleration's direction does not tell you which way the object is moving.
Oh.
Velocity tells you the direction of motion. The sign or direction of acceleration tells you if the velocity is increasing or decreasing in that direction.
Can you give an example?
Sure. Think about throwing a ball straight up. Let's say up is the positive direction. Initially, velocity is positive, upwards,
Okay.
but gravity is pulling it down. So the acceleration due to gravity is downwards,
Yeah.
or negative in our convention.
Right.
So you have positive velocity but negative acceleration. What happens? The ball slows down until it stops at the top.
Exactly. Then it starts falling. Now its velocity is downwards, negative. And the acceleration is still downwards, negative. Negative velocity, negative acceleration.
It speeds up in the downward direction.
Precisely. So the sign of acceleration relative to the sign of velocity tells you speeding up or slowing down. Same signs mean speeding up. Opposite signs mean slowing down. Velocity sign tells you the direction of travel.
That clears it up significantly.
Oh.
And just like speed and velocity, can acceleration be uniform or variable?
It can. Uniform acceleration means the velocity changes by the same amount in every equal time interval. The change is constant.
Like that falling ball, ignoring air resistance?
Free fall is the classic example of nearly uniform acceleration, thanks to gravity, close to the Earth's surface anyway.
And variable acceleration.
That's when the velocity changes by different amounts in equal time intervals. Think about a car in traffic.
Yeah, constantly speeding up, slowing down, sometimes coasting.
Exactly. The driver's foot is modulating the accelerator and brake, so the rate of change of velocity, the acceleration is all over the place. Variable acceleration.
Which leads nicely into the acceleration due to gravity, G. You mentioned it with the ball.
Right, G. It's the specific acceleration experienced by an object falling freely just under the influence of Earth's gravity. We ignore air resistance for the basic concept.
And it has a standard value.
Its average value near the Earth's surface is about 9.8 meters per second squared. Often, for, simpler problems, people round it to 10 meter suits.
And its direction.
Always downwards, towards the center of the Earth. So how you use it in equations depends on which direction you've defined as positive.
Right. If down is positive, G is plus 9.8. If up is positive.
Then G acts in the negative direction, so you'd use 9.8 meters in your calculations for acceleration.
And this G is the same for everything, right? Famously.
Famously, yes. Ignoring air resistance, all objects near the Earth's surface fall with the same acceleration G, regardless of their mass. That's the core of Galileo's insight. The feather and the hammer on the moon idea.
In a vacuum, they hit the ground together.
In a vacuum, yes. Air resistance messes things up here on Earth in practice, but the underlying gravitational acceleration is independent of mass.
It's amazing how these concepts build on each other. Our sources also include some numerical examples, don't they? Just to kind of put this all together.
They do, and they're really helpful. Things like converting units, maybe from kilometers per hour to meters per second, which is often more useful in physics formulas,
Right, the standard units.
or calculating how far something travels if it moves at a constant speed for a certain time, or simple acceleration problems like the car example we discussed.
You don't necessarily need to work through every calculation here, but seeing the scenarios helps connect the definitions to, well, actual moving things.
Absolutely. It grounds the theory in practice.
Okay, so let's maybe try and quickly recap the main points we've covered in this deep dive on one-dimensional motion.
Sure. We started right at the beginning, distinguishing scalar quantities, just magnitude, like distance or speed, from vector quantities, which need magnitude and direction, like displacement, velocity, acceleration.
And we talked about rest and motion being relative, dependent on your frame of reference, and how using the idea of a point particle can simplify problems.
Then we defined one-dimensional motion, straight line movement, and really focused on the difference between distance, the total path length, and displacement, the straight line change from start to end with direction.
Which led us to speed, the rate of covering distance versus velocity, the rate of changing displacement, including direction. We looked at uniform, non-uniform, average, and instantaneous versions of both.
And finally, we tackled acceleration as the rate of change of velocity. We discussed positive acceleration, speeding up, negative acceleration or retardation, slowing down, and the special case of acceleration due to gravity.
Emphasizing that acceleration is also a vector, and its direction tells us about the change in velocity, not necessarily the direction of motion itself.
Exactly. Getting these fundamentals clear is just so important for understanding pretty much any other area of physics involving movement.
Mm-hmm.
And, just for understanding the world around you better.
It really does give you a new lens to see everyday things through.
It does. And maybe here's something for you to think about later, a final thought to sort of chew on.
Okay.
Imagine you're at an airport on one of those moving walkways.
Mm-hmm. Yeah.
How would you describe your speed and your velocity relative to the walkway itself, the belt you're standing on?
Okay, relative to the belt.
And then how would those compare to your speed and velocity relative to someone standing still on the floor beside the walkway?
Ah, different frames of reference again.
Exactly.
Ah.
How did the ideas we've discussed today, especially relative motion, maybe even adding vectors, implicitly help you analyze what seems like a pretty simple situation?
That's a great puzzle. Definitely makes you think about applying these definitions. It's not always as straightforward as just dropping a ball.
It often isn't.
Well, this has been really illuminating. Hopefully this deep dive has maybe sparked some interest for you, the listener, to explore more. Perhaps thinking about how we graph these motions, position time graphs, velocity time graphs.
That's the next logical step, often.
Indeed. Well, thanks for joining us as we dove into the fundamentals of motion in one dimension.